I'm Serge Kernbach from Germany, and I know I'm in a very dangerous position now because I'm standing between you and dinner. The whole stuff what we speak about is non-local phenomena, what we explore. And a very specific part of it is non-local entanglement. So communication over long distances, transmitting of specific properties over long distances. Of course, it gives us a lot of possibilities and it has a lot of implication. It's, of course, a long title for this event. But I would like to give 3 key messages here. The first message is that electrochemical impedance spectroscopy in the basic form or in extended form, what we do, is extremely useful for detecting effect, for characterizing effect in the field of non-chemical water treatment, especially information pharmacology, biofield research, what was told already today, and in this non-local impact transmission, what involves a lot of quantum effects. As this exactly the second point, that's non-local quantum phenomena. It could sound strange, macroscopic system, but currently, there's a lot of research, and European Commission started even a new flagship. And quantum technology invests about 1 billion euros in them, so it will be a lot of new research in this field. And last message, what I would like really to say, it's not, just phenomena recently discovered or 1 year study. Attempt like this, they started from 80s. 83 is the first experiment performed with impedance spectroscopy, and up to now, only published, well-published experiments is over 1,000, in my knowledge. Time is limited, of course, so we just proposed, this workshop. This in Saturday we have a couple of devices here, so we just invite everybody who has some technology or interested to test for a real test of technology. So you can perform, for instance, some biofield test or experimentation with new devices that will be here in this room. So we have 5 devices. We can distribute it in the auditorium. Just, you need to install a software. So just please contact us in the exhibition hall for installing a software. So 5 copies can be installed. And we just, a few hours ago, we had discussion with Konstantin. Because, we have here this exhibition, we have a collection of very different technologies. And it was idea, why not to experiment a little bit with different technologies? And there was a proposal, this biofield, they will take place tomorrow. Yeah, tomorrow, because Konstantin will leave them, okay. Water, because water here is a central point. And of course the question is water, why water here? What is special in water? We use water, at least in this context, as engineers. Water has 4 different phenomena, what's taking place in water, as you know. There's a near electrodes effects, there's a dipole polarization, double electric fields, it's well-known stuff. Ions, so it's ions mobility. It's self-ionization, proton tunneling, what is this kind of phenomena. Of course, easy water. And this quantum effects was taking place up to now. 3 quantum effects are known, and they contribute essentially to this macroscopic, this quantum phenomenon macroscopic system. And we can sense all of different phenomena here by use, electrochemistry. And it seems when we just tune a few parameters, we design system, also engineer the system in a specific way, we are able to sense different effects here in very, very high resolution. I already presented a few times for different electrochemical approaches. Finally, we use impedance spectroscopy. also from our point of view, is this provides the most of feature useful in practical application, everyday application. Also it's more or less classical standard approach. You add this water cell, you apply a voltage, a sense current. But, well, we a little bit extend this scheme. You can apply, for instance, voltage and sense voltage, so with 4 electrodes. Then we use differential approach, so we use the sense differentially between channels. Then we sense not only on frequencies, but we sense on time, what is pretty unspecific, so for impedance spectroscopy is pretty much new. And we have a great resolution here. We are able, we specifically develop mobile device for using in field application. We are able to sense up to nanosiemens and centimeter, also in time resolution. How it's look like? We have here video. I mean, we make sampling in real time. And this is more or less what you see when you make, perform experimentation. You see time resolution, as it's happening in real time, and there's a frequency. And here you can really see what is happening with water, what kind of structures appear, what kind of patterns appear. And we add in this way a new dimension of working with this impedance spectroscopy approach. Well, of course, there's a lot of publication you can find in our page. So, I would like to focus on 3 cases, 3 application cases. The first one, I think, is the most important, this non-chemical water treatment. The reason is European Commission tried to reduce amount of chemicals added in the water, and the more and more strict law in that way. And more industrial producers, they start to replace chemistry by non-chemical approaches. And it's very difficult to sense because you have water and you have water. I mean, the same water. There is no chemical changes here. Then here, especially in information pharmacology, also in the old one and the new one, we observe last year's growth of interest even from pharma companies. So here are quite well repeatable phenomena, and it seems more and more interest is attracted to exactly to this non-chemical water treatment. Just to be clear, what does it mean? In our terminology, I mean, this non-chemical water treatment means 3 ingredients. First of all, you need a kind of source of weak emission. Weak emission could be more unconventional or more conventional. It could be from some field, hydrodynamic cavitation, laser, UV light. Then when it meets a material modulator, it becomes somehow modulated, polarized, and then you can transfer to additional materials. And then when we put here sensors, then we can sense all of these phenomena. It can be embodied in different way. One of typical embodiment, for instance, well-known approach by Luc Montagnier. This another approach, also well-known, firstly applied in 90s by Andrei Bobrov, and use optical emitter. It's a very specific mode. It's a high pulse impulses, about hundreds of ampere here per impulse. And then you have a layer of materials, penicillin, mostly people use, and then water. You can imprint water in that way. Exactly with this technology, hundreds of experiments has been performed. What we, for instance, and currently many people use exactly this approach by using laser. Exactly. And here you have a laser source. You have object, in this video at least as a sugar cube, and then you have water, what you can imprint. And we sense what is happening with water when you perform this imprinting approach. This is a setup. We use in this case electrode outside of the thermostat. And here, when laser is off, there is, no changing. Nothing is changing. Just background recording. And then when laser is off, And we record over 20 different parameters. We record temperature, electromagnetic field, magnetic field, all this stuff is recorded. About 3, 4, 5 minutes after this, we observe a growth of different patterns. And as normally as low frequency patterns, as they start at low frequencies, they grow. And when laser is off, the pattern still grows. There's still active process in water, and we can observe this process. We can make a kind of visual image processing algorithm and try to classify these patterns. So we can really observe what is happening with water. But interestingly, it's not only, this recording of a single container with water, like here. Here, for instance, temperature, you see all these effects cannot be explained by, trivial reasons like temperature. But here, we use a differential measurement. So we perform imprinting of one object and measuring interaction with a second object. We're measuring differentially between two objects. One of this is active and another one is not active. And you see here as the first when we start, and here is a differential measurement now. You see we observe a lot of high-frequency effects. And this affects this interaction between active object and passive object. And then when we switch off, we observe low-frequency components. So you see different components in the fluids that explain it first by imprinting and by interaction between imprinted and not imprinted objects. As again, it's not explained by temperature. There is a lot of experiments. I think we will discuss a little bit more because methodology of this experiment is pretty open. There's an extremely high-resolution approach, but it requires specific methodology. I would like to give, to discuss only two experiments. They are extremely interesting. The first one is a global experiment what was initiated by Evgeny. And the idea was to measure with different approaches, to measure impact of this active CD in this case. And we performed a lot of attempts. At least here, in the one attempt, we just explore what will happen when we put two empty, as a not active CD under measurement containers. And when we activated CD in this way, it's just putting in the laptop and this emission from a monitor, then what will happen in this case when we put some information in CD? Are we able to sense any difference between them? Only informational, so-called informational difference. And this is our first result. Here we just make a spectrogram at 5 different time points. Before experiment, as a first hour, as a during activation, 1 hour after, 4 hours, and 24 hours after. So a kind of time dynamics. And we see here the most intensive impact appear between, let's say, 4 and 6 hours after imprinting. And this is a little bit strange because when it could be somehow explained by trivial factors like temperature or something else, we would expect high impact exactly in this area. And again, it disappears after 1 year, one day. So active in the frame of 24 hours. Here, a result of differential measurement. We measure in the one channel is empty CD, also empty in this activated sense. So empty CD and activated CD. So the difference is, this is a kind of phenomena what we are looking for. And here, that's even visually visible, is again all these phases. In the 1 hour, also in the activation 1 hour after this, we basically see no difference. And we see no difference, let's say, 24 hours after. But here I see exactly the time, also 4 to 6 hours, we see about 10% of difference between activated CD, impact of activated CD, and impact of non-activated CD. This is exactly the point, where I say, it's interesting. And this is not a single effect what we discover. This is another experiment. It's by Impedance. Probably you know this bioresonance therapy. Some medical people use this. And they use for putting some information in this water, imprinting it that way. We performed measurement. There was an exhibition about a few months ago. Yes. measurement 1.5 hours after activation, and you see here is a normal spectroscopy over frequencies, and we see almost no difference. But when we're measuring it 6 hours after, we see a great difference, especially in the low frequencies. And this more or less gives us a little bit indication what is happening and when it's happening. And the most important that you can measure this in reproducive way. This is another example, also in this field of non-chemical water treatment. And this is, let's say, extremely, also in the current situation, is extremely highly discussed. And it seems exactly this approach have a lot of practical issues. And it's about entropy. You know, entropy, that's when you, for instance, dissolve salt, then you see a kind of increasing of entropy. And when you, for instance, crystallization, then you decrease entropy, in a simple way expressed. And there was, in 60s, as a Kozyrev, there was the first one, also from scientific point of view, who discovered that entropy, also this delta entropy, can be transferred in a distant way. So when you just take a system and you can transfer entropy between two systems. There was a lot of experiments later on in the Soviet Union by academic Lazarev. I mean, there's really a lot of people who try to reproduce this effect. It seems it's quite reproducible. The beauty of this thing is unspecific. I mean, it's unspecific. It can be applied to many different systems. Because, like I said, it has a kind of entropic context. Probably that this entropy is a kind of placeholder for something different. So, but nevertheless, we speak in the terminology of entropy. Here is one interesting experiment. Here is a decreasing of temperature. Here is the temperature curves. And here we observe decreasing of impedance. I mean, the dependency between temperature and electrical conductivity is proportional. The decreasing of temperature, decreasing of conductivity. Here we insert a source of negative entropy. And you see a growth of patterns. Then here we remove it, and we observe the degradation of temperature. At least at this point, we expected something like here that we will have here a degradation of conductivity. But we observe here just a change of dependency between temperature and conductivity. It seems all of this stuff related to entropy is able to change dramatically electrochemical properties of fluids. And you know that when you just think about batteries, accumulators, all of this stuff, just changing and influencing system is this way, create great possibilities. We, at least in our philosophy as a measurement lab, we try to test whatever we do in physical methods and biological methods. And this one of this biological sensor, what we quite frequently use is a fermentation approach. So we're measuring fermentation produced by yeast. And we can easily detect either stimulating or inhibiting. And we performed a number of measurements with negative entropy with the sources. And you see there are two measurements. They are strongly stimulating. In two cases, we observe almost equal stimulation. And it's more or less a kind of confirmation about this, properties of unspecific stimulation. When we think more in the way of Biofield, it's only a couple of slides because there was already a beautiful presentation in the Biofield. We observe sometimes people, people just touch a container, we measure temperature, measure conductivity, measure, what is happening. And some people are able to change electrochemical properties of fluid forever. For as long as we measure this. And then the question is, here, for instance, is quite a strong experiment. We remove all these temperature effects. But still, we have a change in the impedance spectra. And the question is why? What is happening there? This is a similar attempt. So a person first touch one container, and then just perform a mental concentration, and I touch it again. And you see the difference here. And so the second time is much more stronger. And this was more or less consideration to create a kind of, let's say, approach to work with these biofield measurements. As a biofield in this case is a kind of, let's say, different impact in different field. Is a physical and, let's say, less physical. That we just person first touch one container here, and we measure this parameter, and then perform a kind of training activities, the different, probably meditation, whatever. And then we observe the second time, and we measure the difference between the first one and the second one. And here is an indifferential measurement. And one of the idea is here why people are put in the water so large difference. So essentially behind thermal impact, essentially behind any capacitive effect, because we are source of negative entropy. And probably here we observe more or less exactly the same phenomena with negative entropy. We just transfer a part of us to the water. I mean, in the long term. Of course, a lot of research in the front of us, but here at least we have a kind of really beautiful tool to work in this way. Most interestingly, of course, this non-local impact transmission, because it's one of the key points of this talk today. Like I said, it could sound strange, yes? There's a quantum phenomenon, macroscopic system. Why? All this distant transmission effect over thousands of kilometers, strange, yeah? But at least, there's a number of high-impact publications deal with quantum phenomenon macroscopic systems. Even, like I said, European Commission published next work program, and now it seems there will be a quantum technology flagship. Up to now, there are 2 flagships. There will be a third one, and each flagship that means about €1 billion of investments for research, for scientific research. So it seems quite. All of these quantum phenomena, they have a kind of strong support. Well, again, what it does mean in our terminology. So we have this emission in whatever region, we have material, we have polarized emission, and now we put a kind of quantum, let's say, quantum entanglements. Yeah? We just put something what can work over the distances. Normally, it's a kind of digital representation, or we just took one object and cut into parts. There's a different way. I will show a few of them. Just to say, it's not something what we create new as of now. All this stuff is known from beginning of written history. It's sometimes in very strange context, but nevertheless they are known. Radionics, it's over 100 years of whatever is happening in radionics, but they used it. One of really scientific, high-level scientific investigation was undertaken in 80s. Also it was one of essential part of Soviet program. And by the way, there was strong lead by Academy of Science, Russian Soviet Academy of Science. And experiment, as the first of this experiment was performed in 96. And there was multiple repetition 90s and so on and so on. And in Moscow, it's a distance 26 kilometers, I assume. And on the receiver side, there was plant tissues, 5 different plant tissues, and they selected only one specific plant tissues, and this was on the emitter side, and that's what they receive on the receiver side. It's a kind of in context of information transmission system. This effect is very simple to demonstrate. It's very easy to demonstrate. Here we have overcooled water. So 4 tubes. Here we have about 10 meters away just LED emitter. And we have, some digital representation of this tube. We select the tube number 2. And here there is some part of the coin that's here. Well, we emit about, 40, 50 minutes. Just in this way, nothing else. And you can see now what is happening. You see? It's just frozen. So, this overcooled water extremely sensitive to almost all kinds of impacts. And exactly this experiment can be repeated, even at home. And just, put overcooled water, put a kind of imprinting system, and see what will happen. And you see that even many hours later, there is no changes in any order of tubes. This effect can be quite easily demonstrated. We performed a lot of, let's say, research at those time at university, so a number of concrete walls that look like this. So here are sensors. You see, it's in a basement, in our basement. And when you just see a video of this setup, you can immediately see it's not something related to electromagnetic emission, it's not something related to any vibration, whatever stuff. And here is a emitter, is again optical emitter, as powered by batteries. There is even no connection to any electromagnetic stuff. There is a kind of result what we observe. You see, there's a background measurement for number of hours, as a really long-term measurements. And then when we switch on the generator, we see a change of trends. Of course, you can ask, how many times did you repeat it? And then I say, yes, it was repeated a number of times. The most largest distance was between Australia and Stuttgart. It's about 30,000 kilometers. This is the diagram what we received. I already demonstrated this several times. And here, just please remark, we have here a jump. I will go to this point later. And by the way, here you see in any cases when the generator in Australia was switched on, we observe in Stuttgart changes of the trend in the systems. This just number of iterations is published. Number of iterations, what we see, it's anyway is going to hundreds of iterations. There was a state of the art, more or less, in this field. Now we, let's say 1 year ago, we asked ourselves, okay, what could be the next step? What could be the next step? And then we created online system, just really in online, everything in online. And here is the impedance spectroscopy. We have theta sensing, microfibril fuel cells. And you see all of this effect, you can observe just in real time. Just in real time. You see what is happening. And here we publish a link, exactly in this container is the electrodes, and exactly this container is used in experiments. Okay, what was the first task? It was a simple task. We have in Facebook a group for public discussions. Everything what is happening here is extremely public. And then one of the tasks was, you see these graphics, you see the changes in the graphs, and just try mentally to change it. And then we publish it over the whole world. This kind of this, there's no operator name, but here is a distance you see as a distance, it's in very, very different countries. And then people, without any training, just people observing the graphs and just with mental concentration, I would like to change it, We receive a kind of, this anyway statistically significant, and we receive about 70% of success rate. Even it was more because some people do not follow the methodology. They put several attempts just in short time. So in real situation, it's even more. But even 70%, just not trained person, having no information, no link, just by observing graph, are able to change it electrochemically. Of course, now the question, why it's happening? What is behind this? And we observe in many cases two kinds of reaction. One reaction is a change of trend. So we have a trend, we record trend for a couple of hours, and then we switch on the generator and you see a change. It's very visible. We don't need to discuss anything here. And then the question, what is the reason why this changes, this trend is changing? The system is thermostabilized, it's no CO2, it's no electromagnetic phenomenon. It's a completely encapsulated system. And we observe a small degradation of electrical conductivity. It seems we have a kind of self-ionization phenomena. two water molecules, they split to two ions. And then, a number of publications say this also created by a fluctuation of electric fields. This is this science paper. And we was pretty much amazed that the reason for fluctuation of electric field that create this self-ionization phenomena is a quantum effects and what's happening in macroscopic system. And so the first assumption is, at least what we think in that way, that fluctuation of electric field in the water have this quantum stuff. Very short second, that in sometimes we observe a jump in the dynamics, and the question is, what is in this case? And in this case, it's another effect. It's a quite well-known proton tunneling effect. So the proton, they tunnel in the hydronium group and hydroxyl group. We again exclude all simple reasons like temperature or kind of bubble, creating. And this is the most important slide here. Here we perform experiment as a long-term experiment that was with Moscow, about 2,000 kilometers, for a long-term non-local impact in terms of days or even weeks. And you see here in the background phase, there was no changes. No single changes for a day. Yeah? And then when the generator was switched on, non-local generator, we observe a number of jumps here. Also, number of these quantum proton tunneling effects. Of course, there's an open discussion in which way it's happening. But it's, there's a kind of new technology what was tested. This is a test, just a person mentally concentrate, as this was in St. Petersburg, concentrate, and we again record for almost 10 hours, and you see no single spike here. And around the time the person just mentally concentrate, we observe this spike in the dynamic. So it seems that persons, and there's not a single experiment, of course there's operations, even that human consciousness, as a kind of indication, has probably this relationship to quantum phenomena. Okay, I'm ready to this. I have only one conclusion. And conclusion is following, this effect, the phenomena, what we described as information imprinting, it's not a really research now. There is a lot of application, real application. And one of this application, metallurgy. People perform this imprinting of this fluid metal. They improve, stiffness of material, flexibility, whatever. And there was a lot of attempt in Russia, Turkey, and Germany. And all this engineer was extremely happy. Okay, yes, we have it because it's much cheaper metal. But after this, there was discussion with lawyers and insurances. And they say, well, when is something happening and will be metallurgical analysis, what they will discover? They will discover cheap metal. Okay, and then you are in troubles. And after this discussion, there was a stop of anything else after this. And the point is, socialization of technologies. We need to integrate all of this unconventional phenomena based on weak effect, weak informational stuff. We need to socialize. We need to integrate in society in different processes, technological processes, and social procedures, like insurance, for instance. This is my key point in the conclusion. Thank you very much.
Thank you.